I was so close to finishing this example problem in the previous video, but we just couldn't quite get there. So let's do a quick recap of where we were and what we still have yet to do. So we're trying to figure out how much energy a freezer needs to pull out of some water in order to create ice cubes at a temperature of negative 12 degrees. So we first found the energy required to take that 20-degree water down to 0 degrees. Then we found the energy required to freeze it and turn it solid. Now that we've got solid ice cubes, we need to find the heat energy required to drop it down 12 more degrees from 0 to negative 12. So our mass is still 1.5 kilograms. The C, the specific heat of ice, is different than the specific heat of water. The specific heat of ice is only 2,100 joules per kilogram degrees Celsius. And we're wanting to chill this ice from a temperature of 0 down to negative 12. So that's a delta T, or change in temperature, of 12 degrees Celsius. So 1.5 times 2100 times 12 gives us heat energy of 37,800 joules. That's the energy required to chill our ice. So we chilled the water, covered up my one there, chilled the water, froze the water, and then chilled the ice. So the total amount of heat that needs to be taken out of this water is the sum of these three. So it's 125,580 plus 499,500 plus 37,800. And so that equals a total of, comes out to like 662,880 joules, but that's too many significant figures. We should really only be using two significant figures here. So that's about 660,000 joules, or we could just write that as 660 kilojoules. That's the energy that the freezer is going to have to take out of that water to turn it into ice cubes at negative 12 degrees Celsius. So let's move on to the means by which heat can flow. We have conduction. So conduction is basically when heat flows through a solid material, like this red-hot steel poker from Raiders of the Lost Ark. The heat will excite the molecules in the steel, which will then excite the molecules adjacent to them, and so on, and the heat will travel down the steel. So this is why if you have perhaps a metal pan with a metal handle on the stove, you might need a pot holder to grab onto it, because the heat from the stovetop will travel down the length of the metal handle, and the heat will flow through the solid material. Convection is another means by which heat can travel. So here we have a fire in a room. We have Indiana Jones and his dad tied up in this room, and there's a fire in the background. That's going to heat up the air, and then they'll feel the heat from the fire because the air in the room has been heated. So convection is basically a way that heat travels through fluids, like gases, like air. And then the third type here is radiation. That's how we get energy from the sun. It travels through outer space. There is no air in outer space. There's no solid material in outer space. So how does the sun's energy get to us? It gets to us through electromagnetic radiation. And so that's the third means by which heat can travel. So it can travel through a solid material, conduction. It can travel through a fluid, convection, or it can travel by means of radiation. So let's first look at conduction, which is the way that heat flows through a solid object. And we have here this diagram to help us visualize this. So we have these two blocks of solid material. One is hotter and one is cooler. And they're connected by this solid piece of material, which has a circular area. And so heat is going to flow from the hot material to the cold material, and it's going to want to continue to do that until both sides are equal, until there's an equilibrium achieved here. And so we can kind of visualize the transference of heat as one molecule colliding with the one beside it, and then that collides with the one next to it, and it's kind of like this chain reaction of vibrating molecules. And if we wanted to quantify the heat flow from one solid material to another with this kind of contrived setup here, the heat flow over time, how quickly the heat flows, is equal to K times A being the area of the material through which the heat is flowing, times temperature 1, the hot temperature, minus temperature 2, the cold temperature, divided by L, the length between the two materials. So that just leaves K. What is K? Well, K is a coefficient. It's the thermal conductivity constant, and it varies depending on what the material. So if we look at this chart and the different substances and what their thermal conductivity K is, we can see that it looks like this chart is arranged according to highest value to low. So again, we've got silver and copper and aluminum and steel at the top. These are all metals. So metals are good conductors of heat, which is why I said earlier copper is commonly used in cooking pans, pots and pans. We don't use silver because it's more expensive, but silver would be actually a better option if we were just looking at its physical characteristics. Economically, though, copper makes most sense. But aluminum also can be used. It's perhaps not as durable as copper. But the point is these metals are good conductors of thermal energy. On the other side, look at the things that are poor conductors: wool, goose down, polyurethane, and air. These are things that we use to insulate. So you might have a goose down comforter on your bed or a goose down jacket to keep you warm in the winter. Wool sweaters keep you warm in the winter. And air is perhaps the best insulator. It is the best insulator on this list. A cavity of air, a thermos, the way it works is it has an inner container and an outer container, and in the middle you have a vacuum sealed pocket of air, which keeps whatever is on the inside insulated. So large K means it's a conductor. Small K means it's a good insulator. So home construction. Homes are an area where you might be concerned about insulation. We add insulation to prevent heat energy in the winter from our heating systems to escape to the outside. So windows, as you can see here in this thermal image, are an area where heat can escape. Glass does not have a very good K value. So there are things you can do to improve the insulation of windows. You can have double paned windows with a layer of air in between them. Air is a very good conductor, or some other gas like argon will give you better insulation. But in this particular example problem, we're looking at just a single pane glass window. It has an area of 2 meters by 1.5 meters and is 3.2 millimeters thick. So we have an inside temperature and an outside temperature of 15 degrees Celsius and 14 degrees Celsius. So not really a huge difference. But we want to calculate the heat that is going to flow through here. So heat always flows from hot to cold. So the heat is actually going to be flowing through this window in this direction, from the 15 degrees to the 14 degree side. So if we use that equation we just had on the previous slide, it's Q over T, the heat flow over time, is equal to K A T1 minus T2 over L. So the K value for glass, if we go back here, is not real good. 0.84 is the K value. 0.84. Our area is 3 square meters. The change in temperature is just 15 minus 14, not a huge change in temperature, just 1 degree Celsius. And the thickness of our pane of glass, the length of the material that the heat is flowing through, is 3.2 times 10 to the negative third. And so if we solve this equation, we should get Q over T of 790 joules per second. So that's how much heat is flowing through this window every second. And that's just with a 1 degree temperature change. So imagine on a cold winter day when it's 0 degrees Celsius outside and 20 degrees Celsius on the inside, that heat is going to be flowing out at a pretty high rate, because the thermal conductivity of a piece of glass is it's relatively, if we go back here to this chart, I know 0.84 might seem kind of small compared to silver or copper, but compared to air, we're comparing 0.023 to 0.84. So that's like nearly 40 times worse. So that glass is a real weak link in the chain, so to speak, when you're trying to insulate a home. So if we want to insulate a home, we might go buy some fiberglass insulation like you see here, or cellulose insulation, or expanded polystyrene. And what you're going to see when you go to buy that insulation on the packaging is the R value. So R value is the resistance to heat flow. So the higher the R value, the better the insulating. Whereas with K value, the higher the K value, the more quickly it conducts heat. Its R has an inverse relationship to K. So a very low K value is going to give you a high R value. And R value also includes the thickness of the material. So if you double the thickness of insulation, you're doubling its R value. And so yeah, you can see here R values of typical building materials. Glass, an 1/8 inch thick pane of glass, has an R value of only about 1. And that actually comes from the air layer that clings to the outside of it, whereas fiberglass insulation for 4 inches of that has an R value of 12, which is much, much better.